Hello Shirin, hello everybody. I'm here from Paris, ready to talk to you about sports and economics based on my book, Be a Champion, 40 Facts You Didn't Know About Sports and Science, that you can also buy in the US.
Many people see sports and math as polar opposites. How do you bridge the divide in your work?
The world of sports is actually full of numbers. When you watch competitions on TV, you see the record, time, velocity, angle. So you are really full of information that we call data. But the point is to use these data to be predictive and to understand performance. And this is where mathematics and equation and deterministic models can be really useful and insightful to understand performance.
Your research explores the mathematics behind Olympic performance. What first drew you to the intersection of elite athletes and mathematical modeling?
As a mathematician, I have been studying problems where you minimize energy. So energy today is really something that people think about, energy expenditure. But there's one form of energy also which is human energy. And my mathematical tools is about minimizing energy that I used to minimize human energy. The point with math is that you can use equations to describe movement and energy and therefore be predictive about performance.
Can you explain for a non-mathematician audience what kinds of models you've built for Olympic athletes and their performance?
The power of mathematics is to couple many laws ruling the world. So when you're interested in modeling running, for instance, there are three laws that we put into equations. The first one is mechanics, movement. It's based on Newton's second law of motion. No need for anything more than Newton's equations from the 18th century, which states that when you vary the velocity, the variation of velocity is related to the different forces that are applied. Second law, energy, conservation of energy. There is energy in your body that you use to propulse yourself. So the power of the propulsive force is exactly equal to the energy coming from your breathing, oxygen, and the energy coming from your muscle and your food, which is sometimes called anaerobic energy. And the last thing is third equation. You are not a robot, so there is a brain, and you have to take into account the brain into the equation. That is, we put into equation motivation, and with this model, we can determine the best time according to the physiology of each athlete. Of course, the power of mathematics with respect to data, the power of equations, is that you can be predictive. That is, you can imagine that you train hard and you improve some of your parameters like your force, like your VO2, that is the rate of oxygen you transform into energy. And therefore, you can understand how performance varies when you train and change these parameters.
In economics, we often think in terms of maximizing utility or profit under constraints like income or time. In your research on Olympic performance, you're modeling athletes maximizing speed or efficiency under constraints like energy, oxygen, and biomechanics. How do you see this parallel between economic optimization and athletic optimization? And what can each field learn from the other?
Because you're a human body, you have a heart and a brain. So effort is related to heart and brain, and it's not as if you were a robot where you can switch the button between on and off. So actually, I have worked with a neuropsychologist in Paris. He's a doctor working with patients who lack dopamine, and he's the one who has built an economical type model to understand motivation. In his case, is a lack of dopamine. In our case, we use it to model motivation in sports. And actually, when you are motivated, it's like a model where you have choices and constraints. And this will be exactly like an economical problem, and is really related to becoming a leader, a champion in athletics or in economy. So there are three important points in motivation. When you're motivated, you are quicker to react, so reaction speed. When you're motivated, you're ready to make an intense effort. You can get much stronger. And the last thing, when you're motivated, you can decide that tiredness is not important, that it can hurt, but it doesn't matter, because you want to reach the goal, you want to be the champion. And this equation that we write for motivation, that we include in our model for performance, is really very similar to an economical problem.
Could you walk us through how that plays out in a specific example? Maybe a middle distance race like 400 or 800 meter? And how does your model help determine what the optimal strategy is under the constraints?
What we have proved is that there are two types of race. Short races, sprints, like 100, 200, 400 meters, and endurance race starting from 1500. So the difference is the following. For sprints, the strategy is to start as strongly as possible. And because you have a brain, the best way to put an intensive force is to put it at the beginning and the strongest possible. This has the effect that all sprints for champions are run with acceleration reaching the peak velocity in the first 60, 70 meters. Even on a 400, which is a lap, sprinters do not accelerate further than 70 meters. That is, they run 330 meters decelerating. So what is the strategy on the 400 is to start as strongly as possible and to limit deceleration. And what we have analyzed is exactly the physiological parameters that influence this acceleration, intense acceleration at the beginning, and that limit deceleration in the last 330 meters. What we have proved as well is starting from a 1500, which is longer, where your oxygen system is reaching a plateau. The best strategy is to start strongly so that the oxygen system is working fast. And then you reach your mean velocity, your pacing, and the best strategy for a long race is to keep energy in order to be able to sprint a little bit, at least to accelerate at the end. So on sprints, they cross the finish line slowing down, whereas on an endurance race, you have to keep anaerobic energy from the beginning in order to be able to finish and even accelerate, which is the best strategy.
Could your models help us think about inequality in sports, how access to training or infrastructure affects outcomes?
What we have realized are things that most champions or international coaches know. But the point is we make this information accessible to everybody, especially young athletes who are training. This type of information is something they do not necessarily know. They haven't necessarily discovered by themselves. And the point of science and publication is exactly to put information at the level of everybody so that young kids, young people can learn and become better in their performance.
How do you think about constraints like fatigue, oxygen use, or biomechanics in your models, and how might those mirror constraints in economic behavior?
Sports modeling is really like an economical behavior because you have constraints exactly as in the real life, just because you come from a real human body that you want to understand. So in the model, you want to minimize time, but you want to also minimize your effort or your fatigue. The point is you want to minimize the interaction between the brain and the muscle, because this is going to hurt you if there's too much. So the main parameters that we take into account are the anaerobic energy that you want to use as much as possible. And during training, you want to increase it, but at the beginning of a race, it's fixed. You want just to use as much as possible of what you have. You want to minimize your fatigue or your effort, and you want to optimize time with all this physiology that you have. So it is what we call in mathematics optimal control problem, because there's always the control by the brain, where your brain can decide anything. It can also decide to not to move, to stay here, stay sitting and do nothing, which is the less tiring thing. But of course, you will not reach the best time not moving. So it's really, our optimal control model is really based on economical behavior, exactly as in the real life, because any choice of a human being is in fact based on economical behavior of what it brings to you, but what it costs as well.
The McKinsey article frames CEOs as elite athletes. From your perspective, what parallels do you see between athletic optimization and executive performance?
There are really similar qualities between athletic champions and CEOs. It's difficult to state all of them, but I would say resilience, curiosity, ability to make a strong effort, to work hard, and in terms of performance, everything is related to what you decide in your brain, in your motivation, in your ability to decide to make something that costs you a lot, that is difficult, but because behind there is an aim and a target that you focus on.
Could you imagine your research being applied to help optimize decision-making or stamina in high-pressure corporate environments?
Oh, it's a difficult question. What I think is that, as a mathematician, I have taken competitive exams. And my vision of it is that taking exams in math or making a sports competition is very similar. So I would say that you have to have the stamina indeed, to the motivation, the self-confidence, the decision that you are going to make it because you have trained and you're going to make it. And the spirit of the leader, the spirit of the champion is really what unifies, I would say, scientists doing very strong and difficult theorems, champions or CEOs. With self-confidence, you know you're going to make it.
Do you think your data-driven performance modeling will become standard not only in sports, but in leadership training and corporate coaching?
I'm not necessarily a good person to make predictions. The point of my research is really to analyze data from that point of view to determine the physiological parameters of a person and make prediction rather on with the type of information we have, that is changes in the physiological parameter, how you should change your way of running a 400 or a 1500 or a 10,000, or what is the influence of a strategic behavior. The point is we write equations, and I'm not sure at the moment how you could write equations in the real life. We're able to model the brain, but this is not necessarily sufficient to go beyond and make the predictions that you would be interested in. Nevertheless, it's always what I believe in research is that it's always new discussions like the one we have today that will influence new ideas, new perspectives, new ways of thinking.
How do you collaborate with other disciplines, like physiologists, economists, or data scientists?
Yes, this work is totally interdisciplinary. So I have worked with an English physiologist. He works in Leeds in England in a university where there is both a research on the one hand, especially sports science, and there are British champions on the other hand. So he was the one interacting with sports people. On the other hand, so I'm a mathematician doing modeling. I've interacted with doctors and neurophysiologists, neuropsychoanalysts in Paris who work on brains and motivation. And in my team, there's also a computer engineer who's coding, that is, who's transforming the equations into simulations with numbers. And so this type of research is really putting into the same field a lot of people coming from different perspectives and trying to analyze things with different eyes. And this is why we managed to get these new models that nobody had worked on before, coupling the heart, the brain, and mechanics.
What's next in your research? Are there new sports or performance puzzles that you're interested in exploring?
Well, next in my research is analyze all the data that we got from the Paris Olympics. So you have a very nice t-shirt with you, Paris 2024. The athletic track in Paris, the Stade de France, was not a standard track. Nobody had told you, nobody had told me, but when I tried to make my model work on these data, I realized it wasn't working. So my first thinking was, where's the mistake? And then I realized that the mistake was considering Stade de France was a standard track. So it was 400 meters long, no problem, but the radius was larger, the straight was shorter, and this made a lot of differences, and especially one. In the 1500, Cole Hawker from the US managed to overtake from the inside, which would never have happened on a standard track because centrifugal force is too strong. He ended the race saying, I don't know how I did it. It's normally impossible to overtake from the inside on the last straight. He did it because the radius was 1 meter larger, and though he couldn't really feel it, he managed to accelerate a little bit and overtake Josh Kerr from Great Britain and Jacob Ingebrigtsen from Norway. So my first point is really now to analyze all these data, get information from our model, and understand better the results of the Paris Olympics. Of course, in the longer term, maybe do it on other sports. I would really very much do things on skiing, as we will have a new Winter Olympics in France in the future. But the trouble with skiing is that it's not an athletic track where you have the geometry. They never go exactly at the same place. And in our modeling, altitude and topography is very important. So, but this could be a long time perspective as well.
What advice would you give to young mathematicians or economists who are interested in solving problems in applied sports and health?
Be curious. Be curious of the world around you. Ask yourself questions, and you will see that many answers come from bridging between different fields. So get interested in many different things. Just learn whatever you can, and you realize that things that you've learned from a field can be used for another one to understand things better. It's very funny to see that many laws in the world are used in disciplines, in fields that have nothing to do from the beginning, but it's just that it looks like there's some kind of unity in the world, and being curious really is something that helps you understand, and you're always happy to understand things afterwards. Something else is that interval training is often useful when you want to train because it improves your ability to change pace, it improves your reaction speed to change everything in your body. And we have seen that sprints in an all-out race, endurance race, you have to start strong, then you have a mean velocity and you have to sprint out. So I would say make your career an endurance race, start strong and think about the sprint at the end. That will come because you will reach a situation where you want to really make the most of everything that you have learned. And it is for sure that qualities developed by champions are very similar to the ones that heroes should train on: efficiency, hard work, curiosity, and using your brain and your motivation to drive you to being the best.
Until next time, teammates, I'm Dr. Shirin Mollah, and this is a Sports Economist. If you enjoyed today's discussion, be sure to subscribe and leave us a review. And don't forget to follow us on social media for more insights in the fascinating world of sports economics. Thanks for tuning in, and we'll see you next time.
Thank you very much, Shirin. Thank you, everybody.